Hello everyone, good morning, good afternoon and good evening. My name is Vishwadeep and I welcome you all on PW GATE channel. Today is the class where we will practice some different kind of questions of the CPU scheduling. We have seen already what type of scheduling algorithms we have. Every type of algorithm we have discussed, their pros and cons, their advantage, disadvantage we have discussed. Now it's the time to take ourselves into that mode where we will use the IO also, which means till now we have learned the basics of how each and every scheduling algorithm will work. Now the practical scenario comes where IO requirement is also there for the processes. Then from running process, okay, I'll explain it here. From running state, if a running process finishes some kind of CPU burst, then goes for IO operation in the blocked state. Once IO operation is done, again process comes into the ready state. From ready state, again it is scheduled for running. If it is having another IO, will go for IO, then ready, then running, and then that particular thing continues. If process completes from running, then it will go for terminated state. So this is what the basic idea we are going to discuss today. Just confirm once if you guys are able to hear me properly. My audio and video are clear for you guys. Can you please confirm quickly? Can you please confirm quickly if my audio and video are clear to you guys, so that we can continue with today's discussion? And I already explained you, from running state, process can be terminated, process can go for IO, but process will go for IO only after completion of its first CPU burst. If CPU burst is, let's say, 5 time unit, currently CPU time gone for 3 for a process, and then process preempted. When a process is preempted, then that process will go for ready state, not IO. Once process will be again scheduled and will complete its complete burst of CPU of 5, then only process will be able to go for IO operation here, and then it will again come to ready state for the running. So this is one of the question we are going to discuss. I will explain so that you guys can understand each and everything. Once you guys are comfortable with what exactly I am trying to do, then we will solve 2-3 questions based on that by you guys. Means practice only we will do in the class of those type of question. Then certain more concepts we are going to discuss. Okay. Consider a process scenario in which each process executes first in CPU, then goes for IO operation, then once again process needs a CPU burst, and then terminates. So the going of the process will be like this: CPU burst, then IO burst, then again CPU burst, then terminated. So 2 times CPU and 1 time IO operation is needed for each and every process. Look at this. P1 process arrives at 0. First P1 process will need 2 time of CPU burst, then 8 time of IO burst, then 5 time of again CPU burst, and completed. This is how the process will work. Following is given process scenario in which for CPU execution system uses non-preemptive SJF algorithm. So for a CPU scheduling, non-preemptive SJF algorithm is used. Consider system has enough number of resources to carry out operation for all processes in parallel at a time. So if 2 processes are going for IO operation, then process 1 will use some other IO device, process 2 will use some other IO device. There is no any waiting for IO device. Basically, there is no any waiting for IO device. Multiple processes can complete their IO operation in parallel, just because we have enough number of resources in the system. Okay, further what is written? How processes are executed and what is the average waiting time for the execution for processes. Okay, average waiting time in ready state. Calculation should be done in ready state. In ready state, how much processes are waiting. That's it. Okay, let's go. First of all, let's execute this process scenario. How to execute this process scenario? At first place, we will check out that what all processes have arrived. Can you tell me what all processes have arrived at time 0? Okay, how will you check it? Now you tell me, what all processes have arrived already in ready state at first place? Arrival means here, from new state to ready state already arrived. In the ready state, what all processes I have for the choice for execution? You tell me. You tell me what all processes arrived. Array, all processes have arrived at time 0 only. So if all processes have arrived at time 0 only, I have all processes available. Among them, which one should be scheduled to run on CPU first? Which one should be scheduled? Based on SJF algorithm, shortest job first, the process with minimum burst time. Minimum burst time is which one? Process P1. So P1 will be scheduled and P1 will run for 2 time unit. P1 will run for 2 time unit. When P1 is running, remaining all processes are waiting. Okay, no problem. Now, once P1's first burst is over, just because it's a non-preemptive algorithm, complete CPU burst, P1 process will complete. P1 is not terminated. It is not finished. It is not completed. P1 will go for IO operation for 8 time unit. P1 will go for IO operation for 8 time unit. When P1 will go for IO operation for 8 time unit, 2 plus 8 till 10, P1 will be in IO. Till 10, P1 will be in IO operation. So IO operation means IO devices. When P1 process is in IO operation, I have liberty. I have liberty of multi-programming that I have already P2, P3, P4 arrived. Among these 3 processes, I can send one process to execute in CPU in parallel of IO operation. That is what multi-programming is. I have explained it in the very first class. Multi-programming says P1 goes for IO, P2 can be scheduled immediately to run on the CPU immediately along with the process P1 is in IO. So, which process I will send for execution next? Smallest burst time process. Smallest burst time is 3. P3 will go for execution. So, P3 will go for execution till 5. When P3 is in execution, IO operation of P1 is going on. Fine. P3 done? Yes. And it will be in IO for 9 time unit. It will be for 9 time unit till 14. So 9 plus 5 plus 9 equal to 14. Which process? P3 IO operation. Now until 10 time unit, P1 is not coming. Until 14 time unit, P3 is not coming into the ready state. Now further, which process is the smallest one? P2 is the smallest one. We can choose P2 next. P2 next till 9 time unit. P2 done. Yes, P2 done. Next is what? Next, P2 will go for IO operation till 5 time unit. So 9 plus 5. P2 will go for IO operation 9 plus 5 till 14. Now at 9, I am not having P1 or P1 again coming back. No, P1 is not coming back. P1 will come back after IO operation at what time? At 10. P1 is coming back after IO operation in the ready state at 10. But look at this. We have only one process remaining in the ready state, P4. So I'll have to schedule P4 only. P4 only. Sir, live lecture hai. Bilkul live lecture hai. It is live lecture. So P4 will be running next. P4 will run next. Plus 6. 9 plus 6, 15. P4 gone for IO? Yes. Till 4 time unit. 15 plus 4, 19. At 19, P4 will be coming back after completion of IO. After completion of IO, when P4 will be coming back, where it will come? Again in the ready state. Now look at this. When P4 was executing in CPU from 9 to 15, at that time, look at this. P1 completed? Yes. P3 completed? Yes. P2 completed? Yes. What completed? IO. All these IO are completed till 15. At 10, P1's IO completed. At 14, P3 and P2 IO completed. So I have only P1, P2 and P3 available. P1, P2 and P3 available. P1, P2, P3. Among these three, P3 is having the smallest burst time. Currently, P3 is having smallest burst time. Yes, so P3 will run for 2 time duration. 15 plus 2. 17. When P3 till 17 done, yes, P3 now completed. P3 now completed. Now at 17, again, P4 is not coming after IO completion. P4 ka IO completion is completing at 19. I am currently sitting at 17. At 17, I have smallest process, which one? P1. So P1 will be scheduled plus 5, 22. Now look at this. Now after 22, you can see P4 already came. Yes, and P2 is also waiting. So P2 and P4 already are there. Now among these two, P4 is the smallest. So P4 will run first till 1 time unit 23. And after that, P2 will come till 30. And this is how all the processes will execute finally. Okay, now completion time. P1, P2, P3 and P4, 4 processes. Turnaround time and waiting time in ready state. Look at this. Completion time, here we will check. P1 completes at 22, P2 completes at 30, P3 completes at 17 and P4 completes at 23. Turnaround time is completion time minus arrival time. All our arrival time 0, 0, 0, 0. So turnaround time 22 minus 0, 30 minus 0, 17 minus 0, 23 minus 0. Waiting time in ready state. Turnaround time minus every execution time. Every execution means whether execution in IO or CPU. Everything when CPU, look at this, look at this. I'll explain you, wait. When P1 is executing in CPU for 2 time duration, P1 is not waiting for CPU in ready state. Here also not waiting for CPU in ready state. When P1 is in IO operation, then too P1 is not waiting in the ready state. So total how much time P1 was executing? 8 plus 2, 10 plus 5, 15. So what exactly this waiting time will be calculated as? Turnaround time minus CPU minus IO burst. Every burst you will have to subtract 8 plus 2, 10 minus plus 5, 15, 22 minus 15 is 7, 30, 9 and 7 is 16, 30 minus 16 is 14 time duration P2 waits. Then here 9 plus 3, 12 plus 2, 14, 17 minus 14 is 3. For P4, 6 plus 4, 10 plus 1, 11, total 12 duration P4 is waiting. So this is the waiting, average waiting time. Let's calculate. 21, 24, 34, 36 divided by 4 is 9. That is the answer. Good evening, good evening. Just check once if you guys are getting the answer. Is there any doubt anyone having? Anything which you could not understand? anything. If everything you could understand, if this particular entire concept is clear, then you solve next question. In this question now, the algorithm is preemptive one. What if we don't include IO burst time? Where? For waiting time, then the waiting time will be calculated as waiting in blocked state total, which includes IO operation time also, and waiting in the ready state. So waiting time will be exactly the time which CPU is not spending in CPU. Sorry, process is not spending in CPU. Didn't get what? I didn't. You did not get. Oh, where you don't want to include this IO burst time? Where you don't want to include the IO burst time? Okay, this one you solve. If you don't include IO burst time in this waiting time, what happens? See, when process arrives, when process terminates, between this time, process may spend time in ready state, may spend time in running state, may spend time in IO state, which is blocked state. If you are subtracting the only CPU burst time, then it is showing that how much time total process is spending here plus here, just because IO burst time you are not removing or subtracting. But if you want to calculate only waiting time, which is process is waiting for CPU how much, means only ready state. In the ready state, process is spending how much time. And that is what we are calculating by removing entire time process is spending here plus removing entire time process is spending here. Here is the question. Okay. Try this one. I'm waiting for 2 minutes here. Okay. I know it will take time. Okay, cool. I guess you might have solved this question. Let me explain this now. Wait. This. Consider a process scenario in which each process executes first in CPU, then goes for IO, then once again CPU. Same kind of question. All IO operation can be done in parallel. Arrival times are now different. CPU burst, IO burst, and CPU burst given. So at time 0, we have only one process P1 arrived. I'll have to schedule it. So P1 will be scheduled. I will run it for one time duration. Its remaining time of CPU becomes 5, and at 1 P2 arrives. P2 runs, P2 is smaller than remaining time of P1. So preemptive SRTF says that P2 will be scheduled. P2 is scheduled. Okay, so P2 should be scheduled. Remaining till 2, remaining time 3, and P3 arrives. At 2 P3 arrives means CPU burst remaining is 1 only. Yes, just because it's smaller one, P3 will be scheduled. P3 is scheduled. P3 scheduled till 3. Now look at this. Only P3 completes its CPU burst first one. Then it will go for IO operation plus 6. So P3 now goes for IO operation plus 6. 3 plus 6, 9. P3 will be in IO. Now, till 9, there is no any other process arriving. So I can complete one of these two or maybe both. Let's see. Smallest process, P2, I can pick it up. Plus 3 till 6, completed. And now P2 will go for IO for just 2 time unit. 6 plus 2, P2, IO. Means till 8. Till 8 only. Okay, till 8, what I can do is I can run P1. So P1 I will run till 8, which is plus 2 time unit. Remaining time is 3. Till 2 plus 2, P1 I am running till 8. And at 8, what happens? At 8, this again process comes P2. Again process P2 arrives in the ready state. When it arrives in the ready state, its burst time is 9. This burst time is 3. This is the smallest one. So this I can continue now. If I will continue it for one time duration, remaining is 2 till 9, then at 9 again P3 also comes. Look at this, P3 comes after completion of this, but its IO or CPU burst 5 is bigger than this. So I will continue P1 only. I will continue P1 and finish it up completely plus 5 only till 11. Now till 11, these two processes completed their IO. After 11, P1 will be in IO. P1 IO 7 plus 11 till 18. Okay. I can pick up one of these two, which is the smallest one, P3. P3 will run till 16. P3 completed. Now P2 will compete. P2 will go till only 18. Why? Just because remaining time 7, just because at 18 P1 comes back after its IO and CPU burst is smaller. So P1 will be scheduled for one duration. After that, remaining time 7 of P2 completes 26. You can now add up all the burst times. 10 plus 5, 15. 15 plus 11, 26. 26, yes, it is correct. Okay, now completion times. Let me just mark down completion time, turnaround time, and waiting time quickly. P1's completion time is 19. P2's completion time is 26. And P3's completion time is 16. Turnaround time, completion time minus arrival time 19, 26 minus 1 and 16 minus 2. Okay, now CPU 6 plus 7, 13 plus 1, 14. 19 plus 14 is 5. 11 plus 4, 15. 25 minus 15 is 10. 7 plus 5, 12. 2. So average waiting time will be equal to summation of these 15 plus 2, 17 divided by 3 is 5.666667. That is your answer. Somebody is getting answer 6. Is there any problem, any query or anything, any kind of mistake I did or you did? Just check once. Just check once. If not, then let's solve this one. This is priority based question again, and it's amazing question. You guys try this one, and if any kind of mistake you are having, let me know. We can discuss. Just try. This is a very, very good question. GATE 2006 question it is. Hello? Yes. Huh. Are you guys able to solve this? This is little tricky question. Little. So if you guys are okay, somebody is taking answer B. Let's try to understand. Same. Arrival time, priority, CPU burst time, IO burst time, CPU burst time given of all three processes. Each process has a CPU burst, IO burst, CPU burst like this. Look at this, the priority. Priority 3 is lowest, 1 is highest, 2 in middle. Further, multi-programmed operating system uses preemptive priority scheduling. Finish time, the completion time of the processes are asked here. Completion time are asked here. Now look at this. At time 0, only one process P1 arrived. If at time 0 only P1 arrived, then there is no any option. We will have to execute P1. P1 middle priority, but there is no any other process. So middle priority process P1 will complete its first CPU burst. First CPU burst completed. So at time 0, P1 first CPU burst till 1 completed. Now after that, P1 will go for IO for 5, which means CPU is free. P1 IO 1 plus 5 is equal to 6. Till 6. Till 6, P1 will be busy. Fine. Now, at time 1, we are sitting currently and there is no any process. Why? Look at this. Next process arrives at 2, P2. So 1 to 2, there is no any process. Idle. CPU is idle. Now what? At 2 time unit, P2 process, at 2 time unit P2 arrives, which is lowest priority process. I don't care. I will schedule it for 1 time duration till 3. Its remaining time is just 2. At 3, P3 arrives, which is highest priority process. The lowest priority process P2 preempted and it will execute till 5. Now look at this. What happens? P3 I will completely execute just because it is highest priority process. Other process will not preempt it. So P3 completes. Yes. Once P3 completes, after that it will go for IO for 3 duration. So P3 will go for IO 3 duration 5 plus 3 till 8. Till 8. Now P1 is not coming till 6. P3 is not coming till 8. Then 5 to 6 I can continue with P2. 1 time remaining, 5 to 6. I will go with P2 lowest priority process just because at 6 P1 is coming. When P1 is coming, after completion of its IO, this one, what happens? Look at this. P1's priority is more than P2's priority. P2 is lowest priority process. So what happens in that case? P1 will be preempted. Still, it's one burst of CPU is remaining, so it cannot go for IO. P2 preempted and P1 again comes and executes. So P1 will execute for how much duration? Till 2. Why? Just because till 8 when P1 completes, remaining time is 2. Oh, sorry, remaining time is 1. What happens? At 8, P3 arrives. When P3 arrives, its priority is highest. When its priority is highest, it will preempt P1 and it will take the CPU and it will execute till 9 and P3 completes at 9. P3 completes at 9. When P3 completes, first we will have to complete P1 again. It will take 1 time duration till 10 just because it is next priority process. Now the P2, the lowest priority process, comes for execution. So P2 completes at 11 its first CPU burst, then goes for IO 11 plus 3 till 14. Till 14, I do not have any other process. So CPU will be idle. Next, after that, P2 will again come for one duration of time till 15 to complete the execution. So completion time of P1 is 10, P2 is 15 and P3 is 9. 10, 15 and 9 is the correct option. 10, 15, 9 is correct option. B option correct. So many of you have got the correct answer. Okay. Next thing. Similar kind of so many questions we have in the PYQs. When process goes for IO, come back again for CPU execution and then terminates. In such kind of question, if you make the Gantt chart, that will be done. If you guys are able to get the Gantt chart, remaining everything is super easy to solve. Everything. Okay, let's go ahead. Next concept is there, CPU utilization. Let's suppose processes whichever we are having, there is no any process which goes for IO. There is no any IO requirement at all. If there is no any IO requirement at all, then all the processes will keep executing on CPU, and then my CPU utilization will be perfectly 100%. Just because every process is available to run on CPU. But let's assume there is only one process. There is only one process and there is 5% chance. There is 5% chance that process will go for IO. Then you tell me, if 5% for 5% time process will go for IO. Let's say 5% time process will go for IO. Then how much is the CPU utilization time? 95%. Why? For 95% process can run on CPU, but for 5% time it will go for IO operation definitely. Okay, but let's say we have two different processes. And both processes can run on CPU one after another anytime. Let's assume both processes are having 5% chance or 5% time 5% time IO operation time. 5% for P1 also, 5% for P2 also. When my CPU will be free? Let us assume only P1 is going for IO, but P2 is available. P2 can occupy the CPU. Yes. If P2 is going for IO and P1 is available for CPU execution, then CPU is occupied. Yes. So what is the chance? What is the percentage of the time when both processes will go for IO? Why? Sir, why are you calculating this? Just because when percentage of time both processes will go for IO, then my CPU will be free. My CPU will be free. So to calculate the CPU utilization, I'll have to subtract 100% minus how is the percentage of time chance that both processes together will go for IO, which is nothing but 5 square. 5% chance, this in fraction, this much. If I will subtract, this is what? CPU utilization 100% minus this one. If I will subtract this one, I'll get the chance that how much utilization I can have. How did you come up with this one, sir? Let's say P is the percentage of time one process goes for IO. Then two processes goes for IO together is P square, P into P. Both processes should go for IO operation together, then only my CPU will be free. Otherwise not. So CPU utilized how much time? This minus how much time is the percentage of time processes are going for IO. So without IO operation, CPU utilization is 1. With IO operation, CPU utilization is equal to 1 minus what? P to the power n. And how that? P is percentage of time process goes for IO, and n is what? Number of processes. If we have 5 process or 6 process, one process is there, this is what CPU can be utilized. Only one process will go for IO at a time. This is my percentage of time CPU is utilized. If two processes are there, this P into P is my probability that both processes will go for IO operation together. Then only my CPU free. After 100% minus this, CPU utilize this much. Then for 3 processes, this much P into P into P. All 3 processes when go for IO together, then only my CPU will be free, otherwise not. One of the processes can, keep my processor or CPU engaged or utilized. 4 processes, n number of processes, this one. This is a formula, please remember this. Okay, there are some PYQs which should be practiced. You can take these questions as homework, just because these are amazing questions, like this one, similar to what we have seen. These are like immediately if you will solve, then whatever you have learned previously or with us, then you can easily understand how the questions are solved. So these are what the questions which should be solved immediately. Why immediately? Just because if you will solve these questions now, you will have a better understanding. Practice should be done when the things are learnt. Somewhat practice should be done when the things are learned, so that your learning will become perfect. And that is why these questions I have brought in the PDF only. Anyway, you will solve PYQs, or you might have solved PYQs, but if you are learning through this particular lecture, then these PYQs you can solve again here at this point of time only. Right? Now another question is this. Look at this. What happens? So the concept is something like this. Round robin we have seen. A process runs for Q duration of time, and between the next process and this process runs for quantum time, some context switch also there. So context switch also will take some time. Yes, context switch also will take time. Then again, after P2, P3 runs for Q time duration, but between P2 and P3, context switch time taken. Then after P3 again, let's say P1 is coming back, context switch time. Then after P1, again P2 is coming, again context switch time. So after each and every process executes, there is a context switch time. Like this. This is the question. Just read the question, understand the question, and let me know exactly what is the correct answer. Are you guys solving this? Just because it won't take that much of time. No answer? Okay, somebody says option A. Okay, let's see. Somebody says option B also. Consider n number of processes sharing the CPU in round robin fashion, assuming that each process switch takes s seconds. So context switch time is s. Every context switch time is s time. Further, what must be the quantum size q such that overhead resulting from the process switching, not from the process switching, is minimized, but at the same time each process is guaranteed to get its turn at the CPU at least every t seconds. Every t second time the process must get its CPU, which means, look at this, after getting the CPU this much here, after getting the CPU here, again P1 get the time here. This should be T. This should be T, bounded above by T. Every CPU or every process should get time or should get the execution every T time unit. At least, okay, which means the maximum time is T. To get its turn at CPU at least every T seconds. After every T second, every process must get the CPU definitely. Okay, so I can calculate the quantum as per this particular time unit T. If quantum will be above, means more. If quantum is bigger, then this particular time, whatever I'll calculate T will go beyond. See, let's say quantum is something. As per quantum 5, I have calculated that quantum is 5, 5 and context switch time is 1, 1, 1. 1 plus 1 plus 1, 3 plus 10, 13. T time unit is 13. So let's say T is 13. I am getting the CPU after completion of P1 and again starting of P1. P1 is getting the CPU after every 13 seconds. Fine. But if I'll include quantum or increase the quantum by one more, my quantum will become bigger, and because of that, my T time unit will not be 13 exactly. It will be more, which I don't want. I want if T is 13 exactly, my quantum should be either 5 or lesser than 5. Quantum should be either 5 or lesser than 5. Yes, quantum should be either 5 or lesser than 5. That is what my calculation should be. Fine. Look at this. Look at this. How many times? If 3 processes are there total, then context switch 1 time, 2 time and 3 times. 3 time context switch is there and 2 time process execution is there. 2 time process execution and 3 time context switch is there. Okay, understood this? So total T duration I am getting as n time all the Q plus n minus 1 times I have context, sorry, n time context switch time, n minus 1 times Q time. That is total T. If I'll increase Q, then this particular t will be even more. Okay, let me calculate that q time unit here. So I'm writing over here this one. N time s, n minus 1 time q equal to t. Q value is t minus ns divided by n minus 1, but my q should be equal to or lesser than equal to this one. Why, sir? Why? Just because if I take q greater, then my value will not be under t time unit. Value will not be under t time unit. So this should be lesser than or equal to t. So that whatever is this much time, q should be chosen in such a way that this particular complete calculation should be either t or lesser than t, so that every process either within t or before that, every process can get the chance again and again and again. So let's assume q is something, t is something 13. If q I will choose 5, fine. Q if I'll choose 4, also fine. Just because 4 plus 4, 8, 1, 1, 1 should be lesser than 13. 8 plus 3, 11, less than 13, no problem at all. So quantum should be lesser than or equal to this much of time, which is option A. Okay. Chalo. Some homework questions I have kept. Why I have kept these questions as homework? So that you can solve them and you can open up your thinking process. And that is what I have, given these questions as homework. Fine. Okay, guys. Thank you so much for the day. We are done with the discussion of the day, and we are done with the process scheduling algorithms. You can discuss all the PYQs by yourself. You can solve them, and most of the questions you will be able to solve. One or two question, if little tricky, you can just go through the reference or solution, but nothing is there which is not doable just because of the knowledge. Knowledge is done. Okay.